Hello everyone, today I am going to deliver a lecture of structural analysis by direct stiffness method for 2D truss. Okay, so before I am going to the deliver on this topic, so I want to show you the some of the what I will say some of the implementation of this method. So this is the Dirick stiffness method. So we can analyze Dirick stiffness method. One is 2D truss, and then 2D beam, and 2D frame or grid, and another we can see 3D truss, 3D frame or 3D grid. So we can see here the direct stiffness method for we can say non-linear problem. So you can see geometry non-linear linearity for beam and frame, and another one plastic analysis of beam and frame. And then we can use the Dirick stiffness method for structural dynamics. So in this today's lecture, I will just cover one the 2D truss. So the laws of the topic we will learn. So of them we just taking the 2D truss. Okay, so before starting the 2D truss analysis, so I want to say why we will going to choose the stiffness matrix. So because of we have been seen here, we can solve the determinate structure, and we can also solve the indeterminate structure. So we can, if the structure is used to force, then we can also solve this structure. We can find out also deflection rotation using this method, using this stiffness matrix methods. Okay, so here is our course content. Today's lecture will cover the Dirick stiffness method only for 2D truss. So in this content, so the content is included. At first we will see the joint displacement and forces, which is including coordinate system, sign conversion of joint displacement and forces, and sign conversion of two-dimensional problem. And then we will see the stiffness matrix for truss member in local axis system, and then we will see the transformation of stiffness matrix from local to global axis, and then we will see the assembly of the stiffness matrix of matrix and load vector for the truss, and we will use the boundary condition, support reaction and member forces, and then we can see the stiffness formation using the equilibrium joint, and last one we will see the problem on stiffness problem on stiffness method for trusses. This is the important, and this is the theory, and other than the mathematical part. So let's see the uh, theoretical part. So before going to the any other, so I want to we should know the what is the stiffness. Stiffness is the extent to which an object resists deformation in response to applied forces. And on the other hand, we have been seeing stiffness is the amount of force which is member subjected to make it deform by one unit. You can see another in finite element analysis. Stiffness is defined being a combination of material property and section property. We know K equal to EI, or we can see P equal to K delta. And here we can see the stiffness matrix. It is the method. What is the stiffness matrix? When you use the matrix, so you can see it is the method which is used to calculate the support moments by using possible nodal displacement which is acting on the beam, and the truss for calculating member forces, since it has no bending moment. In turn, it is to subjected to axial uh, pure tension and compression forces. The steps to solve the analysis structure using stiffness matrix, so you can see lots of we can see analysis. So one of them is finding degree of kinematic indeterminacy, and finding system of coordinate, finding element stiffness matrix, finding displacement transformation matrix, finding system of stiffness matrix and finding system of displacement matrix. So let's start. So our topics, we will see the joint displacement and forces, so which is, we can see first of all we will show the coordinate system. Okay, so we can see here the coordinate in the system 1. We can see x, we can see the x and z are the plane of the surface, and y axis in the vertical. And coordinate system we can see in 3D. That's why also x and y is in the plane system is in the plane coordinate. On the other hand, we can see z is the vertical. So if we see from here, it is taken also from Professor Dr. Anand Sir, University of Asia Pacific, Dhaka, Bangladesh. So you can see the here. So here we can see the figure 1, the coordinate system. We can see here x and z are the plane, and it is widely used, also applied for this process. And we can see here x and y also in the plane. It is used in some formulation. Okay, now we can see the sign convention for joint displacement and forces. So we can see the sign convention for joint displacement forces. We have been seeing in the x and z axis, as we have been seeing this diagram. This is the x and this is the z axis. So if you rotate about to x axis, and we have been seeing here the z and particle is y, so the rotating in z. Another one we can see here in x axis and y axis in vertical, and rotating roundabout on y axis. So all about this here. So the positive, so how can we can take the sign convention? In the rotating in the anti-clockwise, we have been taking the positive direction. It is also from z direction we have been taking the anti-clockwise, and the vertical also anti-clockwise. So all this sign is convention is for positive as the anti-clockwise. If we go to the here, so again here the joint displacement forces, it is all of the anti-clockwise. This is the anti-clockwise, this is the anti-clockwise. So the sign convention and displacement and sign convention in forces, all the displacement because it is denoting u, and force we have been denoting y. That's why we have been seeing sign convention for force and sign convention of displacement. But the main thing is we are taking the rotation in the anti-clockwise, is taking the positive. Okay, now we can see the sign convention for two-dimensional problem. So if we see here that two-dimensional problem is here, the two-dimensional problem. So two-dimensional displacement, we will see x-axis is here and y-axis is vertical. So we will also taking the anti-clockwise is positive. So two-dimensional forces F. So these are the also the anti-clockwise. Okay, now we can see the stiffness matrix for truss member in local axis system. So let's go to the local axis here. Okay, so consider the truss member AB. These are the MAB subjected to the forces XA and YA. These are the forces, and XB and YB. This is the XB and YB at joint A and B respectively. You can see. So assume the length is L. So this is the L length. So modulus of elasticity is, and cross sectional area is A. The axial stiffness of member Sx. So you can see Sx load produced in unit deflection EI by L. Also assume that the member has no deflection of shear. If the displacement of joint A, this is the joint A, and B, this is the B. So UA and B. So UA and B, and UB and BB. So you can see UB, just UA is here. There is UB. This is the UB. and BB is here also. So UA is mean axial deformation, and B means the vertical. These are the vertical deformation. And the similarly we can see UB is a axial deformation. This is the axial deformation, and BB means vertical deformation. This is the vertical deformation. Effect of the result in this case we have been seeing. So if I change the color, we can see UA. We just applied in UA. That's why we are applying the displacement UA. So it will be Sx into UA. And in the similarly, if we apply the UB, so it will be Sx into UB. If we apply, this is the horizontal displacement or horizontal force we have been applied. Now we can apply a force in vertically. So the deflection will we have been seen UV at point A, and if we take the force in here, the displacement will be UV at B. Okay, now we are equilibrium condition we have been known. So f of x A, this is the point of A. So this is the point of A, this is the point of A. So we are taking the wall of A. So we have been seeing x A. So xx UA, this is the xx UA, and then second one we have been seeing there is no axial deformation, that's why 0. And third figure we have been seen here, Sx into B, xx into B, but if it's taken left to right, that's why minus. In the other hand we have been seen here, left to right we have been taken here, xx here, that's why the positive. And fourth diagram, there is no displacement at point A, that's why 0. The same way, if we take the moment, we will be taking the equilibrium summation of f of y, that means the vertical. So we have been seeing the first figure, there is no vertical, that's why 0. Second figure, second, third, fourth, all are the 0 consequently. And axis B, so if we take the moment displacement at B point, so we have been seeing here SS, S and A, which are the taking left, right to left, that's why minus, and 0, there is no axial deformation. And third one we can see here, the axis B in positively in taking the left to right, that's why positive, and third one there is no axial deformation is here. So in this case, if we summarize, or if we equation 1, 2, 3, we can summarize in matrix form. So we can take this here, xx into 0, 0 and 0, and sx into 0, 0. This matrix will be same, and it will be also similar as like we can see the opposite side. That's why it will be minus x into 0, 0, 0 and minus x into 0, 0. It is the opposite. So this will be displacement U, displacement B, displacement B, displacement D, x A, x y, x B, x C. So we can see all of the notation is given here. So we can see we can call here the stiffness, which is K, Lm, L is a matrix, K is the stiffness, L is global. So global stiffness matrix, and displacement global, and the P is load matrix. Okay, the stiffness matrix of member AB in local axis, and displacement vector of a member is local axis, and the force vector in the local axis. So all we have been shown here. So this I have been just writing here. So these are our members. So if we apply UA, then what will be phenomena? So these are the 1, 2, 3, 4. So we have been taking 1, 2, 3, 4, the same as. So we have been taking f of x 0 ux xx ux. So we have been taking left to right xx ux positive, and there is no deflection in horizontally, that's why 0. And third diagram we have been taking minus, because it's going to the left to right. So sx bx, and the number 4, there is no deflection. So we have been finding that. So this is the formation as we have been showing here. The similar will be like this. Okay. Now we can see the transformation of matrix from local to global. Okay, so we've been seeing transformation of stiffness matrix from local to global. um, uh, the theta is always will be count from horizontal member, not vertical member, so you have to remember it that and it will be must be in anti-clockwise. So we've been seen here, here is this local axis, this is the global axis, this is the global axis and global axis here. So theta will be counting here. So if the beam is torting is here, this is the global, so we have to calculate in local. So if we see here a UAL, and if we assume theta is this is the angle is theta, then what will be this angle? This angle will be 30 minus theta, and as this is the theta, then it will be theta. So it will be cos and opposite will be sine. The same as it will be cos and it will be sine. So that's why we will be taking the summation of f of y. This is the f of y. B minus GA sin theta. This is the negative. That's why minus UAG sin theta, and this is the positive in upward. So UAG sin 30 sin 90, which is we can replace sin 90 into cos theta. That's why taking the cos theta. Global axis. Global axis is gravity always is straight line. We can see the xy plane, and local axis is when the member is inclined, then we can see the local axis. On the other hand, the global axis always will be vertical. So if you see here the transformation of matrix, local and global, the member of matrix formed in the local axis can be transformed into global to axis formed by any consideration angle that makes with horizontal. So it will be must be keep in mind in horizontal. The member force in the local axis. So local axis system can be transformed to the global axis system by the considering angle to make it horizontal, not vertical. The local vector and global vector are related by the following equation. So there is some equations we have been already seen here. So if we take the divide this rule, so you can see it will be similar of this, and it will be similar of this as with the opposite. Okay, so you have been seeing that transformation. If we divide this for cell c square, that means cos theta, and s square means sin theta. So we can memorize c square cs s square, and it will also c square cs s square. It will be same as it is as the opposite sign, and it will be also opposite minus c square cs minus s square, and c square cs minus s square. It will be opposite. What is the c? C is nothing but cos theta. We are just taking in the short form. What is the s? S is nothing but s will be sin theta. Okay. Now you can see the assembly of the stiffness matrix and global vector for trusses. Okay, let's see here the assembly of the stiffness matrix and local vector of the trusses. Assemble the global matrix, write the global vector and trusses below. Also write the boundary condition is given. EI is constant. 500 kip per feet. So we have been seen here. Okay. So our formula c square cs s square, c square cs x square. These are the formula. So we must be keep in memories this formula. Must c square cs s square c square cs. So member AB, this is the AB, this is the member. So c square is 1, s square is 0. How we get this? So at first I am taking the theta is 0, AB, because we are taking the moment is here. There is no theta. Why there is no theta? Because we are taking the theta with respect to horizontal. So there is no, it is exactly horizontal. That's why the theta is 0. So cos 0 is 1 and sin 0 is 1. So we can see cos theta equal to C and sin theta equal to F. So if we form this format, C square C S S S square, so C square C S S S square C square C S S S square, we just putting this all the C value 1 and 0 0 minus 1 0 0 and 0, and finding this where stiffness global is A. And similarly we can see the BC. What is the BC? This is the BC, and theta is also 0. So C will be cos theta equal to 0 equal to 1, sin theta 0 equal to 0. And in this form we can just using this formula also here, C square C S S square, C square C S S square. This formula we just putting this formula here and finding this below. The same way we can take the BD. What is the member of BD? If we see, this is the BD, so it will be 90 degree. Why? Because we are taking from horizontal to the vertical, so it will be 90 degree. So C equal to cos 90 degree equal to 0 and sin 90 degree equal to 1. So we are just putting this formula is here, C square C S S square C square C, and finding these values here. And in the similarly AD, where is the AD? This is the AD member. So it will be the theta will be like from this. So theta will be in 10, tan inverse 10 by 10, which is 45 degree. So these are the 45 degree from horizontal. So cos 45 equal to 1 by root 2 and sin 45 equal to 1 by root 2. That means half. 1 by root 2, that means half. So 0.5, 0.5, 0.5, 0.5. I will get, we are just using this formula C square C S S square, or we can use this formula and putting in this formula, finding this value. Okay, now we can see the boundary condition and support reaction and member forces. Okay, let's see here. So we've been seen all the finding all the value, then we can assemble all the G 1 2 3 4 5 6 7 8 and 1 2 3 4 5 6 7 and putting all these values here. Boundary condition we've been seen 1 2 3 4 up to 6 is 0, because there is no displacement, displacement and 0, displacement 0, displacement 0, displacement 0. There is no 0, because this is the roller support. So U5 there is no U5 0, because U5 we can produce the U5 as the roller support. U6 0, U7, U8 is also 0. Okay, we can use the boundary condition support reaction for process. If you go to here 1 1, how will got the 1 1? This is the 1, this is the 1. We've been founding 1, and another 1 we can found, this is the 1 and this is the 1, we've been found 1.5. So 1 plus 1.5, 1 plus 1.5. Number 2, I will get number 2. This is the number 2 into 1, 2 into 1, 2 into 1 is 0. This is the 0, 2 into 1 into 0, and 2 into 1 is 0.5. So we've been finding this way. So we are assembling this in this way and finding this way. Okay. Now we're going to the boundary condition. So if you go to the boundary condition, after assembling the member of stiffness matrix, the equilibrium condition are we have been seen here. I will get 1.5. We have been seen here and previously 1 into 1.5. That means 1.5. So after applying boundary condition, U1 0, U2 0, U3 0, U4 0. How? This we have been seeing this as the pin support. It will be acting horizontal and vertical, so there will be no deflection. That's why 0. U3, U4 also 0, because there will be no deflection. U5 is 0. U6 is 0, but U5 is not 0, because U6 there will be no deflection, is vertical which is U6, but we can see as this is the roller support, so it will be deflected or it will be going to left to right or right to left. That's why there will be no 0 u5. But u7 and u6, u8 also 0. So that's why we've been using this equation. So all the equation after applying, so we will find out. This is the unknown. We have been seeing this is the join. So there is no. So unknown we have been seeing here. The unknown is u5, u7, and u8 because this is the joint, or we can say node. Okay. After this, after applying this boundary condition 6, so we can cross up 1 2 3 4 5. So 1 2 1 1. So this is the 2, this is the 2, this is the 3, this is the 3, this is the 4, this is the 4, and we have a 5. So we will not cut off 5. We have we can cut off the 6. So this is the 6. We can cut off this is the 6. And after remaining, so we will finding this value 1.5. This is the 1.5 minus 5. This is the minus 5. 5 5. So this is the minus 5. This is the minus 5. This is the 1. This is the 1. This is the 0. This is the 0. This is the minus 0.5. This is the 0.5 0. This is the 0 and 2. So in this case we have been finding 5 6 7. So I am just cutting is here 5 6 7 and finding here is here. Why we have been not cutting 5 7 8 or 5 7 8? Just because of boundary condition. So if we see this the boundary condition, so this is the boundary condition, there will be deflection. That's why we cannot say this is 0. There will be deflection. That's why we cannot say the 0. We cannot say the similarly 0. That's why u5 u7 8 say is not 0, but u1 is 0, u2 is 0 because there will be no deflection as the support is pin. Okay, I hope that you can understand. And after this equation we know ku equal to p. So this is the K matrix, and this is the u, and this is the p is applied load, as we have been shown here. Applied load is given is 20 in 10, which is 7 and 8. So that's why we have been using 7 and 8. And after calculating, then we can found u5 u7 and u8. So if we go to here, after boundary condition, we have been finding this value k u into delta. So now we can take the u1, which is 5001.5 into u5. This is the u5. 500 into 0.5. This is the 0.5, and it will be multiplied with displacement 7. So you can see displacement 7, and last one we can see 500. It will be multiplied on the last column of this matrix. So you can see there is a 5, and it will be also, it is u8. This is the u8. So it is the equation 1. The same way we can calculate the equation 2. How we calculate? Let's see. So we can take the second row. So 5 into point minus 5, 5 into point minus 5. It will be multiplied with the first displacement, which is u5. In the same way we've been seeing here, it will be 500 multiplied with 1, and it will be multiplied into 7, and last one and 0. In the same way you can multiply twin. So we have been taking the 3 equation. After getting the 3 equation, we just putting all the equation is here. So if we take the equation is 0.5. So if we take the unknown, and after putting this value, then we can finding three values here, which is u5, u7, u8. Okay, now if we calculate the reaction, what will be the reaction? xa, which is 500 into 5, 1.5, and u1. As we know, u1 is 0 because as we have been taking the boundary condition, so u1, u2, u3, u4 and u6 will be 0 because there will be no deflection. That's why you have been taking that this is the 0. u1 is 0, u2 is 0, u3 is 0, u7 0, u8 0. So we are taking this portion only. So after all is 0, so we have been finding only this member, which is found 8.89, which is xa. Similarly, we can calculate ya and finding 8.89, x equal to 11.11, yb minus 7.78, and yc 5.56 into 12.78 and 3.9, which is 11.88 kg. Now we can use the for the member forces we can use as we know, A divided by L, UB minus UA cos theta, and BB minus BA into sin theta. So let's see PAB. So PAB, that means PAB, this member force we calls A by L, which is deflection, UB minus UA. So we are already calculated UB minus UA, which is called U3 minus U1. So we can see U3. Where is U3? This is the U3 minus U1. U3 minus U1 cos theta, and U4 minus U2. U4. This is the U4 minus U2. Why? Because we are calculating A into B. That's why we are taking this horizontal displace, this point and this point. So horizontal we have seen U1 and U3. So U3 minus U1. So U3 minus U1. And thus it will be cos theta, as there is no theta from horizontal, that's why 0. And another one is vertical, so we've been seen vertical, which is sin theta, also 0. We can, if we use the cos 90, it will be correct, but we've been taking sin theta. It will be U4 minus U2. This is the U4 and this is the U2, the vertical, and funding 500. This is the 0. Every member is 0. Similarly, we can calculate the BC. So this is the BC, as we know. So 500 U5 minus U3. Why U5 and minus U3? Because this is the U5 horizontal last point, which C, and the B point is 3. So C minus B, which is 5 minus 3. So 5 minus 3 into cos theta, as the theta is angle is 0. And U6 minus U4. U6 is vertical, and U4 is also vertical, and funding minus 11.11. So we can similarly calculate the FBD. So if you go to the FBD, this is the FBD. So let's see, FBD equal to U7 minus U3. So if you go to the here, U7 is vertical minus U3, U7 is horizontal, and U3 is also horizontal. 7 minus 7 is cos 90. So we have been used cos 90 as it is taken from horizontal theta. And U8 minus U4, which is vertical, U8 minus U4 is vertical, as taking and sin 90 also. And after calculating, which is found 7.75. In this case, we've been found 7.75. Okay, I hope that you can after applying boundary condition support and stiffness formulation equation. Now we're finding how we'll get this value. It's been shown here. Formulation equation joint. We've been we just seeing how we'll get this value. I'm just showing here. This is the problem I have been solved with you. So these are the problem. So now let's see another problem. Okay, now see stiffness formulation using equilibrium joint. So another way to solve this way very quickly. As we know, 7 into 7, 7 into 7 is very quickly. So we can use upper boundary condition 1, 2, 3, 4, 6, 5 is unknown. Then it will be 0. And only 5, 7, 6 will be known. Okay. So the member we've been taking the, now we're just solving this equation very quickly. I will calculate this. We've been shown the lots of information are taking here. Now we're solving this equation very fastly. I will solve this. So let's see stiffness formulation using equilibrium joint. So this is the solution. So this is the formula. So we have to must be memorized C square CS, C square CS, CS square CS. So it will be must be memorized. So after applying boundary condition, so we've been seeing here AD. So member of AD we've been seeing. This is the AD. So theta we've been found 45 degree. So as we've been knowing, this is the theta from horizontal to here. And C equal to cos 45 into 0.707 and sin equal to sin 45.707. CS equal to CS mean 0.707 into 0.707, which is cos 45 into sin 45. And we've been found 0.50, and C square, that means cos 45 is square, which is we've been square. If we do the square 0.707 square, then we will be found 0.50. Similarly, s square means sin 45 is square, which is 7.707 is square, it will be also 0.50. I will find this 7 in 8. It is our main concern. So if we go, if we calculate here, these are the calculation here. So these are the our boundary condition. We've been seeing U1 is 0, U2 is 0. So U7 and U8 is unknown. That's why you are just taking 7 into 8, 7 into 8. So this is the 1, 2, 3, 4 or 7, 8, or 1, 2, 3, 4 or 7, 8. So it will be acting this formula, C square CSS S square. So C square we've been seeing here 0.50505050. So we are taking this formula. The formula is formatted here. So we can see here another is BD. This is the BD. This member. So after applying boundary condition, so we've been seeing only 7 in 8 is known, and all our we have already applied the boundary condition here. So unknown is 7, 8, 9, and as we know 7, 8 and 5 is unknown. Okay, so we're taking theta is 90. So theta is 90 from horizontal. So C 90, which is cos 90 is 0 and sin 90 is 1. So CS equal to 0 into 1 equal to 0, and C square minus C square means 0 square will be 0, and S square means 1 sin 90 square equal to 1 into 1. So we are just taking 7 into 7. How will get? So if we go to the if we go to the this formula sheet, this is the formula. So we go to the 1278 and 1278 and founding C square CSS S square. So in this way we can using this formula. The formula CD, if we go to the CD, this is the CD. So unknown is 5, 7, 8. So that's why 5, 7, 8. So theta is 135. So if we go to the from here, so 135, but not here. So don't forget it. So it will be horizontal for anti-clockwise 135. So 135 C square, that means cos 135 equal to minus 707, and sin S sin 135 equal to minus 70 plus 707. So CS equal to 0.50, C square equal to 0.5, and S square equal to 5. So if we go here 1576, 1576, then it will be at this formula. So I'm just erasing here, just taking another color. So 1 5, this will be 5 and it will be 5 and 7 6. So we are taking this formula, s square cs 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 s square cs cs. So s square, if we here 0.50 s square we have been seen here, cs we have been found 0.50, and in this case we have been found in here. The similarly member BC, we have been seen member BC. Where is BC? This is the BC. Only 5 is freedom, that's why we are taking the only 5 into 5. And same way assembly. Now we can assembly K add the BD and CD. So we will see K AD BD and CD. This is the AD BD and CD. And funding 576 after putting this below. So we have been seen 0.505, 5 into 5. So this is the 5 into 5 is 1, and another 5 into 5 is 0.5. 1 plus 0.5. This is the 0.5 into 1, which is 1.5. It will be 125. And we can also multiply adding this below 7 into 7 and found the global stiffness is here. This is the K and U, and this is the load. After getting here, we can just taking here multiply with this row with this column and finding this below, and this row will be this column and multiply this below. After solving this equation, after solving these three equation, we will finding U5, U7, U8, which is displacement. If we calculate the reaction in previously, we have been shown here. This is the load. This is the reaction we have been shown here. After applying the boundary condition will be 0, and found 8.89. So same way we can found 8.89. We have been already shown here. The load will be same as it is. Okay, let's see another. If the example C is support settle down 0.1. So the same equation, if we use the C is support settle down, then 0.1 downward, and U6 is 0.10 feet. Then applying BCS condition, all will be 0 and 6 will be found 0.10. So this is the 6 is given below, so it will be not 0. So this is our formula. We must be memorized. We have been seeing here C square CS CS S square C square CS S square. What is C square? C square C square means cos square, and CS equal to cos into sine, and S square means sine square. Okay. So member AD as it is been seen AD. This is the AD, the 45-degree angle C square CSS. So we are using this value and finding this value. And as it is for member BD, member CD, member BC. So after calculating all the stiffness K global, finding this value, but we will deduct the C value, because these are the 6 as the settle down is mentioned in the question. Settle down is mentioned in question. If you go to the here, sorry, there is no. Okay. Okay, no problem. So as we've been seeing, the settle is 0.1. That's why that's where we are not considering C. 0.1 is downward point C. That means this point is 6 is settled down. That's why we are not taking this. We'll just eliminate this. After eliminating this 0.10, then we will finding C below, which is this row will be multiplied this column. So in finding this below, it will be 0. And same way as this, and this. After calculating this, and we will found U5, U7, U8 field square. Now we can see another math examples. So determine the stiffness displacement of joint Z. These are the where is Z, these are the Z, and calculate the member forces where the EI is given 100 kPa. So after boundary BC applying BCS, so you will see U1 is U2. So this is the U1 U2 as the pin support. 3 is not 0, 4 is 0, and 5 is 0, 6 is 0, 7 is 0, 8 is 0, because there will be no displacement, that's why 0. And only U3, these are the U3 is not 0. This is the formula must be memorized. C square CS S square. So after applying this, so we can calculate ZA, that means ZA, that means this member. So only we have been seen 1 is 0, 2 is 0, 5 0, because there will be no displacement, there will be no displacement. Only U3 can be displacement, that's why we've been taking 3 into 3, 1, 2, 3, 4. So 1, 2, 3, 2, 3, 4. So it will be only C square. So only C square we've been seeing 0.70, we have been taking only C square. And the same way ZC, this is the ZC, it will be also same as it is. C square, 3 into 3, C square, which is 0. Now stiffness formula we've been applying here. The deflection we can know K into delta into 93 and found U3 in 0.52. If we calculate the member forces, then we can calculate FZA, this is the ZA. So U1 minus U3, U1 minus U3 into C, 0. C means cos and S means sin. C will be cos will be horizontal, and vertical, which is U2 U4 will be sin. U2 minus U4 will be sin theta, and in this case all the force member will be calculated. So determine another example, you can see determine the displacement of joint Z. This is the Z, the same math I have the same math have been shown here, so just skipping. Identify the zero force member at Truss ABCD, shown the figure, and determine the displacement joint B and C. So this is the B and this is the C. How we calculate the displacement? So this is our formula, we must be memorize. C square CSS C square. So apply boundary condition. How we calculate boundary condition? The pin support will be 0, U1 U2 is 0. The ruler support U3 is not 0, U3 is not 0, U4 is 0, and we've been seeing U5 is 0, but U6 is not 0. U6 as the ruler support, U6 is not given but vertically displaced, and UD we can see 7 and 8 will be 0 also. Okay, let's see AB, the member AB, this is the member AB. Theta is 90 degree, as we are always considering from horizontal to the theta is 90 square, that means cos 90 degree square equal to 0. So S square man means sin 90 degree square equal to 1. CS means cos plus sin equal to 0. So it will be, how will calculate 3, because we have been seeing these are the member AB, only 3 is unknown, that's why we have been taking 3. 1, 2, 3, 4, 1, 2, 3, 4. So these are the 3 into 3 is intersecting here, that's why we have been taking C square. And funding is S square, C square is, as we know, the 0, that's equal to 0. In the same way we can calculate in this here we can calculate this guy here also. Displacement we can calculating here. So the member, after the getting the all the member force, so we can use the K into U. So this is the K into U into P. P is given here, all the force member 58 minus 3. And after putting there 2 below the row and column we putting here equation 1 and equation 2. After solving this equation 1 and equation 2 with the calculate the forming this value. And member force I will calculate A, B, P, C and C, D in the similarly we will shown here. The horizontal that will be cos and vertical will be sin S. The same as we have been shown in the 0 force member in this diagram, as we have been shown this diagram, and determine the displacement of the joint A. So we will calculate the joint A displacement given all the below. So in this case we have been using all this formula. And the same with this another formula, another example we have been shown here for member Z, and after calculating here we've been found this formula K into U into P, and we've been solved this equation and forming the displacement U5 and U6 and also member forces. And the another example we've been seen here, calculating BC stiffness is BC, and assemble this below, applying boundary condition and forming this below. Another one we can see here, given all these 0 force in identifying, then member Z we can found the stiffness, and member ZU, member IU. After all this member we have been using this K into delta, so this is the stiffness U and 5A. After putting this calculating this equation, then founding this equation. After the calculation solving this equation, then we will find the displacement U1 and U3 and the member force also. And this is our example we have been seeing here, also applying boundary condition for quick calculation. So this is our formula, and getting MD, that means M and D, this this member. Similarly DZ, and after calculating all this member, then we will form the K into U into P, and putting this below row into column, then equation 1 and equation 2 solve, then founding the displacement U3 and 4. U3 that means this is the U3, and U4 is sorry, it will be U3, U4 is here. So U3 is O1, and member force we can calculate all the member force. And the same way you can see another example is here. So given all these example, you just take a look and finding all this member. I hope that you can understand. If you have any question, then let me know. Thank you everyone.